So far, most of the functions involving two variables have been generally expressed in explicit form. So that is one of the two variables is in terms of another one, and I have some examples on this next page here. Let's see if it'll bring it up. Here we go. So like the first one, the equation y is explicitly in terms of x. And the second equation, s, is explicitly in terms of t. So there are no other variables over on the right side other than just t. And the same thing is true of the third one. U is explicitly in terms of w. And the last one, y, is expressed explicitly in terms of x. Well, sometimes you'll end up with a function where it's not in explicit form. So like here's an example. You see the x and the y are all mixed together. Well, one thing you can do then is go ahead and rewrite it. Sometimes it's fairly simple to do this. Like here's an example of a function that it's pretty easy to write it in terms of y. So if we would take this equation and solve it for y, we would divide both sides by x. Then we will rewrite that x as x to the negative 1. And then when we find the derivative, we go negative 1x to the negative 2. So our derivative, dy dx, is equal to negative 1 over x squared. All right? Well, that works fine and dandy. However, that does not always occur. Take a look at this next function. So if I asked you to solve this explicitly in terms of x, that means that we would have to solve for the y, get only one y. Well, with a y cubed and a y, we can't do that. So we need another way to find derivatives when you have the y's and the x's or the s's and the t's all mixed together. So that's what we need implicit differentiation for. So let's take a look at some simple examples here. So we want to differentiate each expression with respect to x. Now, when you differentiate, now let's just take a simple function. So let's go back to this. Y is equal to 2x plus 3. Okay, so when we take the derivative with respect to x, on the left side we're doing dy dx. So when you take the derivative of y, we see that derivative form. However, when you take the derivative of x with respect to x, we get 2, and then the derivative of x with respect to x, they basically cancel each other out. And then 3, the derivative of a constant, is just 0. So we get dy dx is equal to 2. All right, so if we're going to differentiate just plain 3x squared with respect to x, then we just take the 2 times the 3, and then the x's to 1 less power. And then that's it. You know, we can show that dx dx, but actually it cancels out. On this next one, though, where we have 2y cubed, and we're differentiating with respect to x, then we go ahead. It's kind of like we have to apply the chain rule to that. So we take the 2 times the 3, so it's like the derivative of the outside function times the derivative of the inside, which is y. So we show that as dy dx. Okay, in this next example, I think I'll write it down here because we're going to run out of room. So when I differentiate this, so the derivative of x is just plain 1, and then the derivative of 3y is 3 times dy dx. So when we're differentiating with respect to x, and we have a variable other than x there, we kind of have to do the chain rule. And so you'll see the author of our book will talk about applying the chain rule to that. So once again, it's like doing the derivative of the outside function. So we just take the 3 times the derivative of the inside, which is y. Now let's take the last one, x y squared. If we're differentiating with respect to x, we have two products here. We have two factors, and so we're going to have to do the product rule when we differentiate. So let's take x times the derivative of the 2y. So it'll be 2 times y to 1 less power times the derivative of y. And then we take the derivative of x, which is 1 times the function y squared, so times y squared. So we would get 2xy dy dx plus y squared when we do that. So you kind of get the idea of how this is going to work. All right, let's take a look here. So to do implicit differentiation, here are the steps that you can follow. So you want to differentiate both sides with respect to x. You want to, and this is when you have an equation then you decide is too hard to just solve it for the y. So you just go ahead and keep everything where it's at. You differentiate. You put all of the terms that have a dy dx on the left side, everything else on the right side. And then you factor out the dy dx. And this is if you have more than one term of y. And then you finally solve for dy dx. So let's see how that works then with this next example. Find the slope of the tangent line to the ellipse, and here's the equation of the ellipse. So see, this might get kind of complicated if we solved it for y, because we're going to have a radical. So we're going to leave it like this, and we're going to differentiate implicitly. So we'll take the derivative of x squared, and we get 2x. And then the 4y squared, we would get 8y dy dx. And the derivative of 4 is 0. So that was the first step. The next step said to put all the terms with dy dx on the left side, move everything else to the right side. So we'll keep the 8y dy dx here. We'll move the 2x to the other side. We don't have to factor out a dy dx because we only have one of them. So then we move on to the last step, which is solve for dy dx. And to solve for it, we would divide by 8y. And if we reduce, we get negative x over 4y. So now find the slope of the tangent line at the point square root of 2 minus 1 over the square root of 2. So here's our formula that we have to use. And our last step then is just to substitute this in for the x and this in for the y. So we need negative square root of 2 over 4 times negative 1 over the square root of 2. So we get negative square root of 2 over negative 4 over the square root of 2. I'm going to invert and multiply by that fraction in the denominator. So negative square root of 2 times square root of 2 is 2. Well, it's negative 2. And then we have a negative 4. So we can reduce that to 1/2. So the slope to this curve at the point here is 1/2. Okay, here's another one. Find dy dx for this equation. So look how tough that would be to solve it for y. So we're just going to keep everything right there and use implicit differentiation. So we're going to take the derivative of y cubed. So that's going to be 3y squared dy dx. And then we get 2y dy dx minus 5 dy dx minus 2x is equal to 0. So now we have 3 dy dx's. So we move everything that doesn't have that over to the other side. I'm going to go ahead and factor out the dy dx and move the 2x over. So if I take out the dy dx, whoops, factor it out, we get 3y squared plus 2y minus 5. And then I move that 2x over. So I then solve for dy dx. So that means I divide both sides by that whole quantity in the parentheses. So we get 2x over 3y squared plus 2y minus 5. So let's say we wanted to know what is the slope of the curve at the point 1, negative 3. So 1, negative 3 is a point on our original curve. So to find the slope at that point, we substitute in the 1 into our derivative, which is our formula for slope. So we would have 2 times 1 over 3 times negative 3 squared plus 2 times negative 3 minus 5. So we would get negative 3 times negative 3 is 9, times 3 is 27, minus 6 minus 5. So that's going to give us 2/16. 27 minus 11, which will reduce down to 1/8. Find the slope of the graph at the point 1, 1. So this one, I just have a y squared. You know, you could solve that one, I guess, and that might be one that you could try on your own, is go back and try this one explicitly. But I think I'm going to avoid it simply because when I solve it for the y, I'm going to have to take the square root, and that might get a little bit ugly. So I'm going to choose implicit differentiation. So we'll start off with the derivative then of the first term. So we would get 4x and then minus 2y dy dx. And instead of writing dy dx, if you don't like that, you can still write the y prime. Okay, that means I need to move the 4x over. So I'll make it a negative 4x. Then I want to divide by negative 2y. When I simplify that fraction, I get 2x over y. And then we want to find at the point 1, 1, we want to find the slope of the graph is we take the formula that we came up with and substitute in our 1 for our x and our 1 for our y. So 2 times 1 over 1. So we would get 2 then. So that would be the slope at that point. So you find the derivative first and then you substitute that in. Alright, so I think we'll end with that. I would kind of like you to go back and try it then on that one, solving this equation for y and then differentiating and see if you come up with the same thing. So why don't you try that next, and then we will see you back in class then. Alright, good luck.